I, Salim, Assistant Professor in Kite Group of Institutions, presenting you measurement terminology. In measurement terminology, first term is our accuracy. The accuracy of a measurement relates to the closeness of agreement between the measured value provided by the measurement system and the true value of the measured. Okay. The true value of the measurement parameters may be in volts, amperes, kilograms, etc. is determined by national standards laboratories working under international agreement and is disseminated by an unbroken chain of calibration. Accuracy is defined as difference between the indicated value and the actual value at room temperature. In most cases, the accuracy is comprised of two main sources of error, the resolution and the linearity. To estimate the expected accuracy of a measuring device, use the root sum of square RSS method to combine the individual source of error. For example, a sensor with 3 mm resolution and 4 mm linearity would have an expected accuracy of 5 mm as given by root sum of squared method. Then we have resolution. The smallest distinguishable increment or smallest change provided by a measurement system, whether digital or analog system are used, this is known as resolution. Means a smallest increment or smallest increment in the input may change the output. This is known as resolution. The resolution of a measurement system is by itself no indication of accuracy. Then precision. The precision of a measurement system relates to the closeness of agreement between measurements made of the same dimensions. It is possible to have a measurement system which is precise but not accurate. Okay. Then traceability. The concept of establishing a valid calibration of a measuring instrument or measurement standard by step comparison with better standards up to an expected or specified standards. In general, the concept of traceability implies eventually reference to an appropriate national or international standards. Means in this case we have to take the reference of national standards or international standards for our measurement, and we have to trace according to that. Then uncertainty. This factor comprises two elements, the first being a systematic error, the second being due to random variation. Uncertainty is an indication of the degree to which the variation in the values obtained when measuring can be reasonably attributed to the measured itself. Uncertainty is normally expressed ratio metrically or in the relevant engineering units like kilonewtons, millimeters, etc. with a minimum 95% confidence level. All errors affecting measurement uncertainty should be controlled by a documented measurement procedure. So to remove these type of uncertainty, we have a particular or a procedure document. Okay. Then we have systematic error. This element is one which is constant throughout the time taken to perform a measurement. This can be defined as the difference between the true value of the measured and the mean value resulting from an infinite number of measurements carried out under repeatable conditions. The major contributing factor is likely to be the uncertainty of the measuring system as detailed in its calibration certificate. Then random error. The second element in uncertainty of a random nature and concerns the inherently variable nature of repetitive identical tasks such as successive measurements of a single term. The random variation in a series of measurement of the same item using the same measurement procedure. Random errors may be due to environmental like temperature, barometric pressure, like for humans like staff training, less staff training, qualifications of the staff and the experience of the staff according to human. Then physical conditions like working condition, like we using a smooth platform and a zigzag platform, both gives me different types of reading. So these are the factors in a random error. Then non-linearity error, that part of instrumental error where a change of the indication or response departs from proportionality to the corresponding change of the value of the measured quantity over a defined range. Various methods can be employed for numerical expression of numeric non-linearity error. The MIRA calibration center generally uses the departure from a least square fit straight line applied to all the data. Like in this case, we have a response, and here is my span in percentage, and here is my stimulus. This is my actual measured data, and I draw a straight line, and according to this I find non-linearity in my system. This is all about my lecture. Thank you.